The components of a computer, the CPU, the memory, the I/O devices, need to be connected to each other to create a complete computer system. A bus is a basic mechanism for system interconnect. A bus operation proceeds in 3 phases. A request is made for an operation, a read or write on memory or an I/O device. The operation is performed on the data. The result is either produced as an output or stored in a register. The result is either produced at an output or stored in a register or memory. A transaction is a sequence of operations to perform something like a read or a write. A transaction is initiated by a unit. Many transactions are initiated by the CPU, but other devices like direct memory access may also initiate. This 4-cycle handshake is a basic building block for protocols. When the initiator makes a request, it moves the request state and sets the INC signal to 1. INC is short for inquiry. When the target sees the inquiry, it moves the response state, sets ACK to 1, ACK for acknowledge, and starts to perform the requested operation. The initiator sets ANK to 0 and waits for a confirmation from the target. Once the target has completed the operation, it sets ACK to 0. At this point, the 2 devices are ready for another transaction. The 4 stages of the cycle are ANK is 1, ACK is 1, ANK is 0, ACK is 0. A timing diagram like this one can describe the relationships between signals over time. A control signal can be at a particular value, 0 or 1. The 2 parallel lines indicate a stable value that may be either 0 or 1. A changing value is a transition from one known state to another. Rising signals change to 1, while falling signals change to 0. An edge is a rising or falling value. A timing event is a more general term for a change in the signal. Timing constraints describe relationships between signals and events. A constraint may just give order. It may also give the time, minimum or maximum, required. A bus is a basic mechanism for connecting the components of a computer system. Some computer systems use more complex interconnect like networks on chips. They may also use several different interconnect systems, such as one for low speed and another for high speed. Let's first look at the signals used to communicate with the device. Request, or REQ, allows the CPU to initiate an operation with the device. Acknowledge, or ACK, is used to respond. Read-write gives the direction of the transfer. The address signals give the location for the transaction. The data signals give the data. A bus can provide connections to a wide variety of devices. Many buses use a clock to synchronize operations. That clock usually runs at a different rate than the clocks for the CPU or for the devices. Specialized circuits may be used to speed up the long wires on the bus and to provide for bidirectional transfer. A bus operation is distributed across several devices. This UML state diagram shows a combined state diagram for a 4-cycle handshake. At the start, both sides of the transaction are idle, given the idle cross idle state. When a request is made, the system moves in the request cross idle state. When ACK is generated by the other side, the system moves to the request cross respond state. When the target of the transaction finishes, the system moves to request cross finish. An ACK puts the system into the done cross finish state. The initiator then sets INC to 0 and the system returns to idle cross idle. Advanced interconnect systems use split transactions to reduce waiting times. The first operation initiates the request, a second operation completes it. Other transactions can be performed in between the initiation and the completion. Here's a Verilog model for the 4-cycle handshake, one case statement for each side. Here's the results of simulating the handshake during operation. The ARM architecture provides an example of a system of 2 different buses connected by a bridge. The AMBA high-speed bus, or AHB, is designed for the CPU, memory, and other high-speed components. The AMBA peripheral bus, or APB, supports slower devices and costs less. The bridge mediates communication between the two. Here's a timing diagram of a write followed by a read on a bus. The address for the transaction is provided as a byte address on the address lines. P-write identifies the direction of the transaction, 1 for a write or 0 for a read. P-select identifies which device is the target. P-enable is set to 1 when the transaction is actually ready. PW-data is used for write operations, and PR-data is used for read. P-ready can be used to extend a transaction. AHB also provides burst transactions that move several data elements at a time. Direct memory access, or DMA, is an important hardware mechanism to speed up long transfers and offload the CPU. A DMA controller is a hardware module that can perform a transaction with limited support from the CPU. The DMA controller has its own request and acknowledge signals. A simple DMA controller can perform only one DMA transfer at a time. A more sophisticated controller may be able to perform several simultaneous transactions. The CPU gives parameters for the request of the DMA unit, which performs the request and then tells the CPU that the request is finished. The CPU can't use the bus while the DMA controller is performing the operation, but many DMA controllers can be programmed to limit their utilization of the bus to avoid locking out the CPU. Here's a UML sequence diagram for a DMA transfer. The CPU sends an initiate command to the DMA controller that gives a source, destination, and length. The DMA controller then performs a sequence of transfers from device to memory. Once all the data has been transferred, the DMA controller sends a complete signal to the CPU. When the DMA transfer is in process, the CPU may be able to perform other useful work if it doesn't need the bus. I/O devices cover a range of capabilities and performance requirements, but there are some general principles about I/O devices. Status registers provide information about the device. Data registers are used to transfer data into and out of the device. Some I/O devices are designed to connect directly to a given type of bus. Otherwise, glue logic can be designed to provide the necessary interface. Some interface circuits require a pull-up resistor. An input device may present an open circuit in some modes of operation. Tying a resistor between the input pin and the power supply ensures that the input pin's voltage will not float to an unspecified value. This circuit operates as a voltage divider. If the device draws current, it can pull down the input pin voltage to a low logic level. If it doesn't draw enough current, the pull-up resistor will pull the input pin's voltage to a high level. Many microcontrollers provide general-purpose I/O or GPIO interfaces that provide a simple way to do easy interfaces. Each general-purpose pin can be programmed independently as either an input or an output. The pins can be configured by writing to the GPIO configuration register. A memory controller has two roles. It manages the parallelism in the DRAM to execute memory operations efficiently, and it manages the complex timing requirements of memories. Many memory controllers can accept several transactions. They'll try to order the transactions to most effectively use the memory. Memory controllers are also designed to provide the required timing. They can receive timing parameters from the DRAM devices in order to adjust their operation to what memory is installed. Thanks for watching.